Okay, sorry, took me a second to get caught up. How's everybody doing? Okay, all right. So today starts chapter 3, matter and energy. So we'll be looking at that a little bit today. Then again on Tuesday with the lab. Next week's lab is all about energy and temperature and that kind of stuff. So any questions from the homework or things that are bugging you before we go into new stuff? Good. All right, well, if you come up with stuff, always send me messages on Slack or through email if you have questions. My office hours tomorrow starting at 9, and I'll be there pretty much all day till middle of the afternoon. So come by if you have any questions or if you want to work on some problems or anything like that. Our first quiz will be on Tuesday, so right after the holiday. We'll have a quiz right in here at the beginning of class, and that will cover everything up through this point. So mostly it will be about measurement and unit conversions and density. Okay, so let's talk about the next part, which is matter. So what is matter? How do you define matter? Anybody have a good or not good way of defining that? Have you heard that term before? So what do you think of when you think of matter?
Solids, liquids, and gases.
Solids, liquids, and gases. So what are all of those things? Like, yeah, they have mass. So stuff, anything that has mass, that's matter. And we're going to look at two different ways of classifying them. So first, we'll go with what I said there, which is solid, liquid, and gas. So those are known as states of matter. And what is the difference between, say, a solid and a liquid? Do you know what a solid is? Do you know what a liquid is? So what's the difference between them? Yeah.
Aren't the atoms more compacted in a solid and then the liquid are more like free-flowing thing?
That's usually true, yep. There's some exceptions, but in general, the solid atoms or molecules, particles are more closely associated, more closely together, and the liquid, they're a little bit further apart, so that's true. But what if we couldn't see the molecules? How would you know if something was a liquid or a solid?
Solids hold their shape, liquids.
Yeah, and that's how they're defined, is that solids hold their shape and liquids don't. The way that we write that is that we say a solid has a definite or defined shape and volume. So when we have this block, which is 10, it's 10 by 10 by 10, so 1,000 cubic centimeters. We can say, first of all, this is always 1,000 cubic centimeters or 1 liter. We can also say that it's always a cube. It always looks like this. It has edges. There's a clear point where it starts and stops. And depending on, it doesn't matter where I put this. If I put this inside of this beaker, it doesn't fit anyway, but if I can put that inside of the beaker, it wouldn't change its shape just because it's in a beaker. If I put it in my bag, it wouldn't change its shape because it's in a bag. So a liquid's different. A liquid still has a definite volume. Like if we have 100 milliliters of water, we have 100 milliliters of water, that doesn't change. But its shape changes depending on what container it's in. So a liquid, we would say, has a definite volume, but takes the shape of its container. Another way of saying that is an indefinite or undefined volume. but it's defined by its container. So if I pour the water, if I take 100 milliliters of water and I put it in my bag, it takes the shape of the bag. If I put it on the table, it tries to spread out, take the shape of the table, and so on. All right, so that's solid versus liquid. What about a gas? How's a gas different from either of those? Yeah.
The gas doesn't have a definite shape.
It doesn't have a definite shape, that's true. So what's the difference between a liquid and a gas?
No shape or volume.
Yeah, it doesn't have a definite shape or volume. The gas takes the shape and the volume of its container. So if I have a 250 milliliter beaker, what is in this beaker right now? Air. How much air? 250 milliliters, right? There's 250 milliliters of air in here. If we super pressurize that air and pack a whole ton more air into there, it's still 250 milliliters. It's going to weigh more, there's more mass in there, but the volume is still the same because the volume is dictated by the container. So the gas not only takes the shape of the container, but also takes the volume of the container. Any container full of gas is going to have exactly that much gas in it. And that's what makes it different from a liquid or solid. Now, the reasons behind these things have to do with the forces between the molecule. The solid is going to have the strongest forces, the liquid's going to have middle amount, and the gas is going to have no forces. Or we could say the liquid has weaker forces, and the gas has no forces at all, effectively, between the molecules. Now, whether that has to do with how close the particles are to each other, it does, but it's not that simple. Does anybody know of an example where a solid, the stuff is not packed as tightly as it would be in the liquid? Ice is an example of that. How do you know that it? Because it floats, right? Remember the density stuff? Ice has a volume, has a density a little bit lower than water, so it floats with just the corner sticking up in there. And that's because ice, the water molecules actually aren't packed together quite as tightly as they are in water. Now that's an exception. Most things, it goes the other way. Most things, the solid is packed much more tightly, but water is a weird exception for that. Okay, so this is one way of defining matter, solid, liquid, or gas. There's another way that we define matter, as we did on, did we do it? No, I'm all confused. No, I don't think we did. I was gonna say in lab, but the lab was about density, it's different. Next week's lab will be, and that is to split it up into composition. So talking about composition of matter in these different categories. And I think it works well to do kind of a tree or a flow chart type style when we talk about this. So let's take matter at the top. And here's all matter can be divided into two categories. One category is pure substances. What do you think the other category is? You had to guess, yeah.
Mixtures.
Mixtures, right. Either something's pure or it's a mix of some other things. All right, so how do you tell if something is pure or is a mixture? You know, I'll take your silence as that you know the answer is that it's really hard to tell and it's not easy. And there is no easy rule about what makes something fit in one category or the other. So we're going to break it down into two more categories, which actually help us to figure out what the definitions of those two broader categories are. So each of these is going to have two groups underneath it. Pure substances can be in two forms, either elements or compounds. And mixtures can also take two forms. Homogeneous mixtures and heterogeneous mixtures. Okay. And these are the four groups we're going to put stuff into and define it. So let's start with the purest of the pure, the elements. What does it mean that something is made, that something is an element? Are we talking about like fire, air, water, those elements? Probably not. What's the last one? Earth? You know, like the four old, like the pre-science four elements. Now we're talking, what are we talking about when we say elements?
Like an element from the periodic table, like.
Yeah, like those things, right? So if something fits into the category of being an element, a pure substance and an element, what we're saying is that that thing is made of only one type of atom. It's made of only one type of atom. What are some examples of like everyday or not so everyday, but things that are tangible things that would fit in that category, that are just elements? Can I think of one? What's a substance that's an element?
Copper.
Copper, sure. Right. So if you have a copper pipe or a copper wire or a copper plate or any of that kind of stuff, copper pot, that's just made of copper. It's pure copper. It's just an element. The only type, I mean, assuming it's pure, the only type of element in there is copper elements. Yeah, what else? Aluminum. Is that what you said?
Yeah.
Yeah, okay. Aluminum. So like aluminum foil or aluminum cans or aluminum, I don't know, what else is aluminum? Cars, pots, pans. There's a lot of stuff. Right, so those are just made of aluminum, assuming it's pure again. That is just aluminum atoms. They don't have to be metals. Those might be the most obvious ones for us. Something like oxygen. Oxygen is a pure element. It's O2. There's two oxygen atoms in a molecule, but it's still just oxygen, so it's considered just an element. Hydrogen, same thing. Nitrogen, anything that fits nicely into the periodic table there, we call that an element. All right. So those are the elements. So then what are compounds? Compounds are probably the trickiest one, at least that's been my experience asking questions about this for a while. What is special about a compound that makes it still a pure substance, but not just an element?
It's like made of several elements, but no matter like how much of it you grab, it's still going to be like an equal amount.
Right, so something about like a constant composition of some different elements. Yep. We usually define this by saying that compounds are made of two or more elements chemically bound. And that's really the important main point here. That the elements aren't just sort of mixed together. They are interacting in this fundamental way where they're like stuck together. And in a later chapter, we're going to talk about chemical bonding and what that means and what all that actually applies to. But for us, the way that we really define this is a compound is something that if you broke it down any further, if you separated anything, you would have a completely different substance. So let's take water as an example of a compound. Water is H2O. It's made of hydrogen and oxygen chemically bound together. If you take the hydrogen or oxygen out, if you separate that and you have hydrogen and oxygen gases, that's totally different. Hydrogen gas, oxygen gas, neither one of those things is like water at all. So by breaking it down, you've completely transformed it to a different kind of substance, and that's what makes it a compound. That you can still be totally pure. Water is totally pure if it's pure water. So it's still a pure substance, but it's made of multiple atoms. If you try to break it down further, you have a totally different substance. So what are some other compounds like that?
Sodium chloride?
Sure, sodium chloride, salt. Again, that is a pure substance made of sodium atoms and chlorine atoms. But if you broke that down anymore, you'd have something totally different. Sodium by itself is a metal. Chlorine by itself is a gas. So very different from salt. Others, some other ones. You know any other compounds? Really any molecular compound, like anything that has atoms mixed together into a molecule. So sugars like glucose would be a compound. You know, any organic molecules. A protein is a compound, even though it's really big and has hundreds and hundreds of, or thousands of atoms in it. So those are the compounds. All right, so those are the pure substances, the elements and the compounds. Compounds tend to trip people up because they see those different elements and think that it should actually go in the mixtures category. So don't let yourself get stuck there. If the elements are bound together to make one type of a substance, that is a compound, and that is still a pure substance. Okay, now let's move over to the other side and talk about the mixtures. What do you think is the difference between a homogeneous and a heterogeneous mixture? You know, ideas? Well, first of all, what's a mixture? Now that we've defined our pure substances, what do you think a mixture is? Yeah.
Like different substances that are not chemically bound.
Yeah, so different substances that are mixed together, not chemically bound. So somebody want to give me an example of a mixture? What is something, maybe something around in this room that is a mixture?
Tea.
Tea, sure, tea is a mixture. What's in tea?
Water and tea leaves.
Water, tea leaves if they're still there. You can take them out, but there's still stuff in there, right? There's other molecules, there's flavors, there's colors, all that stuff. So tea is a type of mixture. Which category would that go in? Homogeneous or heterogeneous? Yeah, it kind of depends if you leave the tea leaves in there or not, I think. So let's define these and then we'll look at some examples. So a homogeneous mixture is one that has the same composition throughout. And a heterogeneous mixture is one that has, we can say, we'll use some fancy words and we'll say different compositional domains. What that really means is you can see the different parts. So if you want to write, you can see the different parts. If that's easier, go ahead and write that. So I have this T here. It is, and I'll let you guys, if we can see, I'll let you guys decide if my T is homogeneous mixture or a heterogeneous mixture. Yeah, you can't really see. Let's look at it. So what do you think? Homogeneous or heterogeneous?
Hetero.
Probably hetero, right? Because you can see the tea leaves sitting in the bottom. So that means that's that different compositional domains. Here's the liquid part, here's the leaf part. So that's definitely a heterogeneous mixture. If I poured the tea off so that you just saw the liquid, that would be a homogeneous mixture because it would just all look like the same liquid. You wouldn't say, oh, the caffeine is over on this side and the water is over here. It's all the same throughout. That also kind of illustrates that determining whether something is homogeneous and heterogeneous is not necessarily straightforward. It's not something that always just has a right answer. Something can fit in both categories depending on how you see it or how you describe it. I think there's some that we can be pretty clear about, like if tea is a little bit controversial, then we could probably say coffee is a homogeneous mixture because you usually don't have your coffee beans still sitting in your coffee. If you do, you're probably doing it wrong. I don't know, maybe it's good, I've never tried it. But even if you put like milk or sugar in your coffee and you stir it up, that's homogeneous because you don't say, okay, the milk is over here, the coffee's over here, and the sugar's down here. It should all be distributed throughout. A heterogeneous mixture might be something like coffee with rocks in it. Does anybody ever drink coffee with rocks in it? You're probably also doing it wrong if you have rocks in your coffee, but you know, it's possible, I guess. So again, you see that different domains. Somebody in my other class said chocolate chip cookies are heterogeneous, but sugar cookies are homogeneous because they don't have the different parts to them. But then someone else said, well, but what if the sugar cookie has frosting on it? And then it just became a big debate, so we just left it at that. We'll put chocolate chip cookies on that side. Other homogeneous mixtures, we might just say all solutions where something is dissolved in something else is generally referred to as a homogeneous mixture. So you've got salt water, that would be a homogeneous mixture. And we always think about this as like solids dissolved in water, but that doesn't always have to be the case. There are other ways to mix things too, like air. Air is a homogeneous mixture. What's in air? What are some of the things in air? You know? It's like one thing that's in air. Yeah.
Oxygen.
Oxygen. What else? Carbon dioxide. What else is in there? You know?
Nitrogen.
Nitrogen. Yep. Water vapor. Some other random gases. All that stuff's mixed together. And it's homogeneous because it's, again, the same throughout. It's not like the oxygen's over here and the nitrogen's over there, whatever. It's all mixed together, all mixed throughout. Other homogeneous mixtures like solids, so things like steel is a homogeneous mixture. Do we know what steel is made out of? What is it mostly? Yeah. Do you know what steel is? Like, I mean, have you seen steel? It's like a metal, probably what your car is made out of, right? So steel is mostly iron, Fe, but it has a lot of other stuff in it too, because pure iron doesn't really have the mechanical properties that would be useful the way that steel is. So it has carbon in it, it'll have some nickel, some zinc, other things like that to give it some different properties, make it harder or softer or more resistant to impact or less resistant to impact or more flexible. You can control that by adding all these different elements, and that gives you a homogeneous mixture, sometimes called an alloy. Another one, gold, like gold jewelry, depending on how pure it is, can fit in one category or the other. So anybody know what the purest gold is called? It's like the most pure gold that you can get. Yeah, who said? What was it? 24 karat gold. So 24 karat gold is pure gold. There is nothing but gold atoms in 24 karat gold. Is anybody wearing a bunch of 24 karat gold right now? Big heavy gold chains worth millions of dollars? No? Okay. Yeah, me neither. But there's a couple of reasons for that. It's not just because it's super expensive, but you can't really make jewelry out of 24 karat gold because it's too soft. 24 karat gold, you could bend with your hands. So if you tried to make jewelry out of it, you'd just be wrecking it all the time. Not only would it be expensive, but it wouldn't really hold up. So instead, we put things like copper and silver in with the gold and make alloys of that gold. And that makes it much stronger and much more resistant to damage. And those would be homogeneous mixtures. So something like 14 karat gold, which is a mixture of gold, zinc, or not zinc, silver, and I believe copper. There are some different formulations of it. That will be stronger. It'll also be a lot less expensive. So that's what our gold jewelry will likely be made out of. That is not a compound because there's no real chemical bonds between those metals. You could melt those metals and separate them back out from each other from that alloy with the right equipment. All right, so you feel good about this classification mechanism? Okay, great. So let's talk a little bit about the other side, the other thing that we care about besides matter in chemistry, which is energy. Excuse me. What's energy? Something that no one in this room has right now. Seems like maybe. Yeah, it's another one that's kind of hard to define, right? Technically, we can define it as the capacity to do work. And that work can take a lot of different forms. So when I take my bag and I lift it up, I am transferring energy from myself to the bag by then putting it on a higher spot. The bag now has more capacity to do work because if I let go, it comes back down and it transfers its energy out to the surroundings, out to the rest of the world. So that's what we mean by energy is capacity to do work. By transferring energy from one thing to another, you allow that thing that you transfer to do different kinds of work. But there's also like chemical energy. So a molecule might have energy, and then when it reacts, it transfers that energy out to create heat or to do some other thing or to make something or whatever. So those are all ways that energy can be transferred. There are two main categories of that. Or 2 hours and transferred? I just blanked out on that one. There we go. So just 1 hour? Just 1 hour? Okay. I don't know why that looks weird to me. Probably the cold medicine again. Is it 2?
2 total.
2 total, but like 1 in the end? Okay, yeah. All right. So energy can be transferred in 2 ways. One is via what we call work, which is a force over a distance. So like, oh, this isn't going to be good, but let's try it anyway. So you push the box along, right, like that. You've done work by transferring your energy to that box by moving it. Okay, so you've force over distance. We're not going to worry so much about that kind of work in this class because that's more of a physics thing. So if you're going to take physics, you'll talk about that kind of work. The one that's going to be more important to us usually is heat. So heat is not the same thing as energy. Heat is the transfer of energy. So energy can be transferred by taking the energy from one thing and moving it to another thing. How do we know when energy has been transferred via heat? How could you tell that?
The thing that's receiving the energy is hot.
Yeah, so one thing is going to get colder and the other thing is going to get hotter. If something gets hotter, it is receiving energy. If something gets colder, it is giving energy or transferring energy away. Okay. So, I don't have a cool picture idea for this one. Anybody have one?
Hot over flames.
Oh, what?
A pot over flames.
Sure, that's a good idea. So you've got a pot. Flame. Is that a flame? Can you tell that's a flame? Never good at this. Trying to draw the grates. That's not really what it looks like. All right, you get the idea. So in this case, how is the energy being transferred? Can somebody kind of describe it? So when you heat water on a stove, where is the energy coming from initially?
The heat, like fire.
All right, so where's the fire coming from? The gas, right?
Yeah.
The natural gas is burning, and the heat from the burning gas is being transferred to the water or oil or whatever you're heating up for the food. So that's chemical energy that's contained within those bonds of the gas that's been put there from, mostly from plants from billions of years ago, that is then being released and turned into heat, and via heat, transferring the energy to your food. All right. So we have two words that we associate with energy transfer, or with heat transfer. Exothermic and endothermic. Anybody know what those words mean?
Exothermic goes out, endothermic goes in. Right?
Is that what you're going to say, Jim?
Yeah.
Yeah, exothermic means going out, endothermic means going in. But what does that mean? Out from where and in from where? So the language we use is to say, endothermic means that heat goes from the system to the surroundings. And endothermic is the opposite. The reason we use those really general words is because depending on how we define our system and our surroundings, we could have different answers. And so those have to be done carefully. Here's an example. So you put an ice cube in a drink. Has anybody ever done that? Something you've experienced? Okay. So what happens?
The ice melts.
The ice melts. What else happens?
It gets all wet on the outside.
All right, it gets wet on the outside. What causes what? The drink gets cold, right? That's the point of putting the ice cube in there? Okay. So if the ice cube is our system and the drink is the surroundings, is that an exothermic process or an endothermic process? The ice cube is the system, the drink is the surroundings. Which way is the heat going? Into the ice, right? Because the drink is warmer to start with, and then the heat goes into the ice. So if the ice cube is the system, then that's endothermic. Ever see how that works? Okay. But that was arbitrary. I could have switched that. I could have said the drink is the system. The drink is what we care about. What happens to the drink? Well, from a drink standpoint, it's an exothermic process because the drink itself is giving off heat to the ice cube. So depending on how you define that, you could go either way. Another example. Get me more. What happens when you sweat? Let me give you a basic summary of the process. Not like all the physiology of what creates glands and whatever, but just like what's the basic thing that happens?
Your body's cooling itself off.
Your body's cooling itself off. So how? Why does sweating make you cool yourself off?
Releasing heat.
All right.
Away.
How? Right now? Your body creates the sweat, right? Goes onto your skin. Then what happens?
Like it evaporates.
It evaporates, right? And that evaporation cools you off. Evaporation cools you off because it takes heat to evaporate something. So if the system is the sweat and the surroundings is you, is sweating an endothermic or an exothermic process? The sweat is the system, you are the surroundings. How is the energy being transferred? Which direction? Yep. It's endothermic. How do you know?
Because your body is the source of the heat and it's going to the surroundings.
But we said that your body was the surroundings. Yeah, sorry. So if your body is the surroundings and the sweat itself is this system, the heat is going from your body into the sweat, right? That's why it's cooling from your body to the sweat. So that is endothermic from the standpoint of the sweat because that's getting the heat. But if your body is the system, if your skin is the system, and the sweat is the surroundings, then it's exothermic because your body is giving off the heat to the sweat to make it evaporate. So depending on how you define that, it kind of goes either way. In chemical systems, it's a lot easier. We don't usually have to worry about that. Because what do you think is always the system in let's say that there's a reaction that gets hot. So what is the system in that case? Anybody? So in a chemical reaction, the system is usually what do you think? Go ahead. Take a guess at it. No guesses? Right. The system is usually the compounds themselves, the chemical compounds. So the system is the chemicals themselves, the surroundings is everything else. So let's say you do some reaction, put some stuff in a test tube, and it gets warm. What is that indicative, an endothermic or an exothermic process? How do you know? So you do some stuff in a test tube, you touch the test tube, and it feels warm. What happened? Was it an exothermic thing that happened or an endothermic thing that happened?
Exo.
Exo, yeah. How would you say that in this kind of language of what's happening. Where is the heat coming from and where is it going to?
The heat is coming from the chemical.
Yep.
Going into whatever's in the test.
Yeah, right. So the heat is coming from the chemicals themselves, from the bonds really, which is where the energy is stored, and then going into the solvent, the test tube, your hand, all that stuff that you feel as being warm. So then if you mix some stuff together, and we're gonna do this on Tuesday, if you mix some stuff together and it gets cold, what does that tell you? There's endothermic. It's the opposite. Heat is coming from the surroundings, from your hand, from the solvent, whatever, and going into the chemicals. Yep. All right. So what if we wanted to be more precise about this? What if instead of just saying it's exothermic or endothermic, we wanted to actually measure the heat that's transferred? How do we do that?
Measure the temperatures before you do the reaction.
Mm-hmm. So we use this thing called temperature to measure heat transfer. Temperature is useful for measuring heat transfer, but temperature is not a direct measurement of heat itself. So temperature is not a measure of energy. It's not a measure of heat. It's actually a measure of average motion of molecules. But we use it as kind of, we need like a starting place and an ending place so that we can talk about how heat is transferred. Because when something transfers heat to something else, as we said earlier, one thing gets colder and the other thing gets warmer. So if we can measure that using temperature, we can say something about heat. So what do you know about temperature scales? Anybody know any? Fahrenheit, Celsius, Kelvin? Have you heard of those? Any of them? Some of them? Okay. What's the difference in them? Which one do you like the best? Fahrenheit? Everybody? No Kelvin fans here? What do you like so much about Fahrenheit?
That's what we use.
So that's what you're used to? Just don't like to change?
It's what we understand.
So you understand? Yeah, we all kind of have a basic sense of like what this temperature means, what this temperature means, like what it feels like, that kind of thing. Sure, so I'm gonna copy this picture from the book. Because it's easier than trying to draw it. That compares the three scales and I think does so kind of nicely. All right, so let's look at these three temperature scales. Excuse me. We've got a thermometer in boiling water with different scales, but the thermometers are all the same size. What do you notice? What are some differences or similarities that you notice about the scales themselves, the little black marks that go up the thermometers? What do you see?
There's more check marks for Fahrenheit.
The what?
There's more lines.
There's more lines for Fahrenheit than for the other two. Everybody see that? What does that mean?
It's more exact.
Yeah, maybe if that's your thermometer, that you have a little bit more precision that way. What does it tell us about the difference between a Celsius degree and a Fahrenheit degree?
There's so many Fahrenheit degrees in the
Yeah, a Fahrenheit degree is smaller than a Celsius degree. So look at the ranges that are expressed here. You've got the freezing point of water and the boiling point of water on these three different scales. So in Fahrenheit, that's 32 to 212. Celsius, it's 0 to 100. And Kelvin, it's 273 to 373. So in both the Kelvin and the Celsius scale, you've got 100 degrees between freezing water and boiling water. But in the Fahrenheit scale, you've got 180 Fahrenheit degrees. There is another difference also, and that is the offset point. In other words, where 0 is. So where is 0 in the Fahrenheit scale? Did you say 0? Yes, thank you. That's true. That's correct. Can't argue with that.
Is that wrong?
Whereabouts is it in this diagram here?
Below freezing.
It's way below freezing, right? If something's 0 degree, if the temperature outside is 0 degrees, that's way below the freezing point of water. That's really cold. You know, that's like the salt on the road doesn't even work kind of temperature. So really, really cold. 0 degrees C is the freezing point of water. So that's much higher on the scale. And then what's 0 Kelvin?
The coldest.
The coldest, yeah, yeah. It's called absolute zero. Way colder than the Ice Age. More like space. And even space isn't quite absolute zero. What is that a measure of? Why can't there be anything lower than that? Do we know?
Molecule 7.
Yeah, so temperature is a measure of molecular motion. And not molecular motion like zooming around, just like vibrating, like that. Everything, like atoms and everything, are always moving a bit. And the more they're moving, the more energy they have, the more kinetic energy they have, the higher the temperature. So absolute zero is when molecules stop. And you can't get any colder than stopped. You actually can't even really get to stopped, but you can get really, really close. So that's absolute zero. So the Kelvin scale is mostly useful when you're dealing with really, really cold stuff. Because anything in normal temperature ranges that we feel is like way up in the hundreds, yeah?
It's impossible to reach absolute zero because everything transfers heat, right?
Yes, right. So you can't actually have no heat. Because anything you would do would end up transferring heat somehow. Yep. Right. So, Kelvins are really useful for really cold temperatures. Also, calculations, because having a scale that can go negative can screw you up when you're trying to figure out formulas and stuff. Think about all the other measurements we make. Temperature, or not temperature, all the other ones. Length, mass, volume. Do any of those have negative scales? They don't, right? You can't have negative milliliters, you can't have negative grams, at least not without meaning something else. So in that way, it kind of messes us up when we have negative temperatures if we need to use the temperature in a calculation. So we'll often use kelvins for that. Also notice that a Kelvin is the same size as a Celsius degree. So they only are offset by a certain amount. But by a number, yeah, by 273 degrees. So a Kelvin degree is always 273 degrees higher than a Celsius degree. To go between Celsius and Fahrenheit is a little bit trickier because not only do we have to correct the offset, because 0 Celsius is 32 Fahrenheit, but we also have to correct for the degree size because a Fahrenheit degree is smaller than a Celsius degree. So we have to do both of those things. And then another weird quirk of the system here, notice that Celsius and Fahrenheit scales are measured in degrees. So you have that little circle that means degrees. But kelvins are not. Kelvins are a unit, like meters or grams. So we don't say degrees Kelvin, we just say kelvins. So that means we can have millikelvins or centikelvins or kilokelvins, that kind of stuff, just like we can with grams and meters and everything else. It's a regular old unit. All right, we're going to talk a little bit about converting between these scales, or among these scales. One thing that's going to help us with that is if we know some basic landmarks on the scales. And these are ones that you should know, at least in Celsius and Fahrenheit. Maybe not in Kelvin, probably doesn't really matter, but Celsius and Fahrenheit, you should know the boiling point of water, you should know the freezing point of water, and you should know normal body temperature. Reasons for that is when you're converting, well, I mean, there's lots of reasons to know stuff, but one reason is that when you're doing the conversions, if you're way off, if you use the wrong equation or you type something in your calculator wrong, you can tell. So if I say, how much in Celsius is 80 degrees Fahrenheit? And you come up with, you type in your calculator and you come up with 80 degrees Fahrenheit is 105 degrees Celsius. That should make no sense to you. That should make you think, wait a minute, that can't be right. Because 100 degrees Celsius is boiling point of water, and 80 degrees Fahrenheit is way lower than that. So I must have done something wrong. I'll have to figure out what I did wrong. Let's look at converting among the temperature scales. This is one conversion that we can't just do the way we've done all our other conversions. We can't just set up the factor label thing and stick in some factor for temperature. And it's because of this offset. We need to multiply and add or subtract, so it doesn't work as nicely. I'm also going to say for this part, you don't have to memorize this. You don't have to be able to do this just cold. You just have to be able to use the equations when they're given to you. Okay? Not something you have to remember. So the first one, the easiest one, is between Celsius and Kelvin. The temperature in Kelvin is the temperature in degrees Celsius plus 273. So that's it. Once you've got your Celsius temperature, you just add 273 and get the Kelvin temperature. So then how would you get the Celsius temperature from the Kelvin temperature? Yeah, just subtract 273. The other ones is where I might get a little bit weird. So if we want to go Fahrenheit to Celsius, it looks like this. The degrees Celsius is the degree, or wait a second, I used T, let's use T's again. The temperature in degrees Celsius is the temperature in degrees Fahrenheit minus 32, so we set it to 0, and then we divide by 1.8. Wait a second. Yeah, that's right, yeah. The key to this one is sometimes your calculator will mess you up if you don't have a fancy calculator, or if you do have a fancy calculator, actually. You have to do the subtraction first before you divide, and nicer calculators automatically do order of operations for you, which means they divide before they subtract. So if you take your nice graphing calculator and you just type in, let's say you wanted to convert 32 degrees Fahrenheit to Celsius. So that should be what? Should be 0, right? Because that's freezing point of water. So 32 minus 32 is 0. Divided by 1.8 is 0. So that's 0. If you type that in your calculator, 32 minus 32 divided by 1.8, the calculator is going to divide by 1.8 first and give you something like, I don't know, 18 or something, 17 or 18. And then it's going to do the 32 minus 18 and give you, yeah, something else, right? Negative 14, sorry. Negative 14, which is not 0. So you have to make sure to do the subtraction first when you're doing that. And then the last one, Celsius to Fahrenheit. The temperature in Fahrenheit is going to be 1.8 times the temperature in Celsius, and then after you multiply, you add 32. All right, let's try this. We'll grab some from the homework here. Try this one. The highest recorded body temperature that a person has survived is 46.5 degrees C. That's pretty hot. Calculate that temperature in degrees Fahrenheit and in Kelvins. So see if you can use those equations to calculate that temperature in both Fahrenheit and Kelvin. We'll see if we get close.
Good brain,
What?
good brain board.
I don't know. It did say survive. It didn't say was fine. So that's sometimes, there may have been some issues there. I don't know. You guys mind if I sit down? I hurt my back. It feels a little bit better if I sit down. Part of the fun of getting old. All right, got some temperatures. What did you come up with in Fahrenheit?
115.7.
That's pretty high body temperature, right? Anybody get something different? All right, that looks about right. So when we would get that number, we would say, does that make sense? Does that seem reasonable? If you know that normal body temperature is 37 Celsius and 99 or so Fahrenheit, then you know that this is above that, but not that far above that. So that seems like it's in the right realm. Let's see what happens if you plug it in the wrong equation. Oops. Let me get my calculator. So let's say we wanted to go Celsius to Fahrenheit, but we accidentally used this top equation. So we would have gone 46.5 minus 32 divided by, so we should do that first just in case. 46.5 minus 32 is 433. Nope. Okay, 46.5 minus 32 is 14.5 divided by 1.8 is 8 degrees Fahrenheit. So if you had done that on an exam or something, look at your answer one more time and say, wait a second, 46.5, that's above body temperature. There's no way that's 8 Fahrenheit, right? So you think about it and then you're, oh, maybe I used the wrong equation. Okay, so now I can go back and fix it. All right, what is that in Kelvins? Say again, sorry.
319.5.
319.5. Yep. All right, you think you can do that? Again, you don't have to remember these equations. You just have to be able to use them appropriately when necessary. All right, I don't want to get into specific heat right now. Let's look at a couple other questions. One other concept. Another way to classify things is to talk about their physical and chemical properties. So we didn't really talk about this, but let's see if we can come up with some definitions here. We'll start at the top. Identify each of the following as a physical or chemical property. Gold is shiny. Is that a physical or a chemical property of gold? It's physical. How do you, like everybody knew that. How do you know that? So yeah, so something you can look at and see of the material is probably a good definition that that's a physical property. Okay. What about the next one? Gold melts at 1064 degrees C.
Physical.
Oh, that was like pretty evenly split. But the people who said physical thought about it for a little bit longer. So what do you think? How do we determine that? Those of you who said chemical, why chemical?
Because it's a reaction that's happening.
It's a reaction that's happening? Okay. Well, so those of you who said physical, why physical? It's a physical reaction? Okay, a physical change. But how do you know? Like, what is it? Yeah.
You're not changing the substance itself.
Yeah, that's really the key here. So in a physical change, the substance is not changed. So gold stays gold. And that's why melting, boiling, freezing, that kind of stuff, those changes of states are actually physical changes. Because you're not changing the basic identity of the compound itself. And so it's a physical property. What about gold being a good conductor of electricity? Physical or chemical? Physical? Agree, disagree? Don't know? Maybe. Yeah, that one's a physical property too. It's true that the chemistry of gold determines how it's going to conduct electricity, but that observation that it does conduct is not have to do with how it changes as a compound. It does not have to do with what gold does to other chemicals. So then D, when gold reacts with yellow sulfur, a black sulfide compound forms. What do you think that one is? That's the chemical property, right? You see why that is? We're now talking about how it reacts with other chemicals, how it changes upon reacting with other chemicals, upon reaction with other chemicals. So that makes a chemical property. Okay, so now for this next part about the candle, I want you to look at each of those four. We're not going to go through them together now, but now that we've talked about it a little bit, I want you to yourself write down, pick for each of those. Is it a physical or a chemical property? And then we'll talk about it. Everybody pick one? All right. Candle is 10 inches high, 2 inches in diameter. Which one do you think that one is? Physical, that's pretty clear, right? Not talking about any kind of reaction there. Candle burns. That's chemical, right? Because how do you know? You can't unburn a candle? It's true. Yeah, like it turns into something else and then goes into the air. So smoke or whatever you want to call that. Carbon, if it's perfectly burning and pure oxygen, it's going to release carbon dioxide and water. But smoke and other particles and things like that. So it's changing its identity. It's turning into something else. C, the wax of the candle softens on a hot day. That's physical. That's related to melting. And then the candle is blue. Physical, right? Now, if the candle turned from blue to another color, if it changed color, that's probably evidence of a chemical change, of something chemical happening. But just it being blue is really a physical property. Okay. Let's stop there. Have a great long weekend. Again, come see me tomorrow or send me a message if you need anything. And we'll have our first quiz when we get back on Tuesday. Yay.